Hi everyone and welcome back. In today's video, we are solving the lead code problem called the case lexicographical string of all happy strings of length n. First, let's understand what happy string actually means. A happy string follows two simple rules. The first rule is the string can only contain the character A, P, and C. The second rule is no two adjacent character can be the same. So this one ABC is a valid string, is C valid string, only B is a valid string, and so on and so forth. While strings like AA, PAA, or AB, APBC are not happy strings because we have two adjacent characters. Two adjacent characters are the same. Now, the problem gives us two numbers, n and k, where n is the length of the string and k means we want the kth string in lexicographical order. And if there are fewer than k happy strings, we simply return an empty string. At first glance, this problem looks like a classical backtracking problem. But here is the interesting part. We can actually solve it in O of n time without generating all possible strings. So, in this video, I'll walk through the brute force idea, why it works but it's not optimal, and finally, the key observation and the optimized solution. So, let's get started. First, the brute force idea. The most natural solution here is backtracking. I have already submitted the solution here. Let's go through it as it's not the main solution for today's video, so I will not go on writing it step by step. So first, we build the string character by character. Like, first we have our main function, so we call the backtrack function, and in this function, it takes the string, variable string, and the length of the string. The variable current string is responsible for concatenating the character one by one and making sure that it doesn't have two adjacent characters. And each time we call backtrack, we first check the size of the current string, and if it's equal to n, that means that we reached the limit of the string length, then we will place that created string into our result vector. So each time our current string reaches the length of n, we place that string in our result vector. Otherwise, we loop from A to C and check if the current string is not empty, it's already having a previous character, and our current character, like A or B or C, doesn't equal the last character. If this condition is true, we will continue. Otherwise, we will append that character to our current string. And then calling back trace again and again with the newly appended or newly created substring, and so on and so forth until our vector result contains all the strings or all the happy strings. And finally, after that backtracking is complete, we check either if our key is greater than the result size, that means that the case string that we are searching for is greater than the size of the result. That means that we don't have that happy string. Otherwise, we return the result of k minus 1. So again, the backtracking idea that we build the string character by character. At every position, we try the three possible characters, A, P, and C, but we skip any character that is equal to the previous one. So if the last character we placed was, for example, B, the next character can only be A or C. This automatically guarantees that the string remains a happy string. Once the length of the current string becomes equal to n, we simply add it to the result list. And because we always try characters in the order A, then B, then C, the generated string will automatically be in lexicographical order. Finally, after generating all valid strings, we just return the case element in that list. Although the backtracking solution works correctly, it's not optimal. Let's analyze the number of possible happy strings if, for example, n equal 10. Or before moving to the example, let's analyze the number of possible happy strings. So to create a happy string, the first character is, we have three choices for the first character, A, P, and C. And for every next character, we only have two choices because it can't be equal to the previous character. So the total number of happy strings becomes 3 multiplied by 2 to the power n minus 1. For example, if n equal 10, so 3 multiplied by 2 to the power 9, that will give us 1536. The brute force solution generates all of them, even though we only need one specific string. So, can we do better? Yes. The key idea comes from understanding how these strings are distributed. So, let's organize the happy strings by their first character. We have three valid characters, so we will have group 1 that start with A and group 2 that start with P and finally group 3 that start with C. Now here is the important observation. Once the first character is fixed, the remaining n-1 position can each choose between two characters. So each group contains exactly 2 to the power n-1 string. That means we can skip entire groups instead of generating them. So let's have an example. If n equals 4 and we fix the first character, so if n equals 4 and we fix the first character to A, in this case, our group will look like A and after that followed by 3 vacant positions. So now we need to fill the remaining 3 positions. A character can't equal the previous character. So for every position, always have two possible choices. So if our previous character here in this case is A, that means that the next character can be either B or C. So we will have A, P, and or A, C, and two vacant positions. Now, if the string is AB blank blank, then that means that the previous character is B, then we have two choices, either A and C, and if our string starts with AC, we have two choices, which is A and B. That means that our newly generated strings will be ABA blank and ABC blank and ACA blank and ACB blank. So far we have 4 strings. Now, each string again has 2 choices. So, after adding choices for each string, the final result will look like. Okay, let's copy them to save time for this video. And this is the final result for the all the strings that are starting with A. So we have 8 strings here. So again, why this formula works? Because if we have a fixed character, for example, A here, then the remaining character will equal n minus 1 equal 3 in our case, and each position has 2 choices that are different from the previous character. So the numbers of strings starting with A will be equal 2 multiplied by 2 multiplied by 2, or it can be equal to 2 to the power 3, which is 8. That's why here we have 8 different strings. Uh, And as we have said, this is in case we have A here as a fixed character, but we can start with P and C. So we have 3 different groups. So the groups that start with A will have 8 strings, and the same. The groups that start with B will have 8 strings, and the group that start with C will have 8 strings. That means totally we will have 3 multiplied by 2 to the power n, sorry, to the power n minus 1, and that will equal 3 multiplied by 2 to the power 3, which is equal 3 multiplied by 8 equal 24. So instead of generating all the 24 string, we can skip groups. For example, if k equals 15, and as we have said, we have 3 groups when n equal 4. Let's say again here, when n equal 4, we have 3 groups, and each group has 8 strings. So if k equal 15, then we can skip the first group and then removing the contribution of this group from k. So the new k will be equal k minus 8 equal 7. That means that the case string or the new case string now is the 7th strings in the second group. So the answer starts with P. This is the core trick behind the O of n solution. So now let's move to the code. First, I'll define a variable. Let's call it total, that represents the total contribution of the n, or of all the happy strings of length n. So as we have seen, that equals 3 multiplied by 2 to the power n minus 1, and I can write it using the shift operation, n minus 1. This is equivalent to 3 multiplied by 2 to the power n minus 1. Then I'll make a quick check to make sure that k is still within the range of the generated happy strings. So let's, for example, in this example, we have seen that we have uh, 24 happy string, but let's say that the k equals 25 or 50. That means that we can't get that case string. So we need to check here if k is greater than total, then we will immediately return the empty string. After that, I'll define a vector of character. Let's name it characters, and that will contain all the valid character A and P and C. I'll use this vector to loop in each character and see if we can append it to the current string or not. And also, I'll define a dummy character, let's call it previous, and I'll define it as the hash character. Now I loop from I equal 0 till the length of the string till n, and I'll increment that by 1. Then I'll while for character C in our vectors character. So I'm looping here on each character to see if I can append it to the string or the current string or not. So first, I need to check if the character or the current character equals to the previous, then I'll continue. So this to make sure no two adjacent character are the same. Then I will calculate how many valid strings can be formed if we choose that character C. So I'll define a variable called remaining that will represent how many characters still remain that represent the blank characters here. So how many character is occupied and how many still blank. So let's define remaining as n minus I minus 1. And I will now calculate the contribution of that character. I mean how many happy string can be formed if this character is fixed. So let's name it count, and that will be to the power n, where n or the new n here is the remaining. And now I need to check if I have or if I ought to skip this group, or that means that this character is the one that I have to build our kid character upon it. So if k is greater than count, that means that we can skip this whole group. So the new k will equal k minus equal count, else I build my string. So let's define here a variable called result that will hold the final result. So here result plus equal our character C, and then I need to set our previous character to C. That will help in on my next check. and then break. And finally, after the loop, I return my result. Now let's run it to make that it's error free. Okay, and submitted. And as you can see, it beats 100% because the type complexity here is of n. So again, let's compare the two approaches. The backtracking solution has a time complexity of approximately O of 2 to the power n, but this optimized solution only processes each position once, so its time complexity is O of n. And also it uses a constant extra space, not like the backtracking where we have to store all the strings or all the valid happy strings in a vector and then return the kth happy string. And that is the optimized solution for today's problem. This problem is a great example of how understanding the structure of the solution space can eliminate the need of brute force. If you enjoyed this explanation, make sure to like the video and subscribe to the channel for more algorithm and problem solving explanation. Thanks for watching and I'll see you in next video. Bye.